time. So in the morning session, we'll talk about the motivation, what are the magnetic materials where you need NDE, and principles of the magnetic NDE methods, which there are three, slight variations of each other. We talk about three different methods: the flux leakage. Then we talk about the Barkhausen noise and magnetoacoustic emission. It's very similar to acoustic emission we discussed. And in the afternoon, I'm just going to talk about some example of a project in magnetic NDE. And again, when we get a sponsor-funded project, it's not just on developing the method is already known, but essentially for a particular type of test geometry, how do you adapt flux leakage to that, and then go through the whole thing, right from sensor design, generating signals, analyzing signals, and coming up with the end result. So most of the projects that we do are involve everything. Okay. So we will discuss that in the afternoon. So afternoon, I want to keep it light and short. So motivation, where do you encounter magnetic materials which need NDE? We have steel, we know that it's most important, strong material that is used in many infrastructures. And pipelines is one of the commonly used, common application for steel, railroads, bridges. You have rebars and concrete made of steel. So wherever you need strength in strengthening structures, you use steel. And one of the disadvantage of steel is that it corrodes. You have moisture, it corrodes. And when it corrodes, it cracks. So it's important, NDE of these steel structures is very important. So what we see here again is an oil rig, and this is steam turbines. So there are many different types of damage that occurs in steel. Okay. In fact, we have a 2-semester course on magnetic materials because there is so much to know about the material side of magnetic structures. Again, it's not exactly the real details I probably wouldn't know, but to the extent what is needed for any NDE person to know is what we look for. So you have, when you look at pipelines, there are 300,000 miles. It's not 300 miles. That's a mistake there. Pipelines, you have, right from the oil where the oil, where it is in the field where the oil is collected or gas is drawn, to the place where then it is distributed. So that's the transmission from, say, California to the East Coast is 2,000, 3,000 miles. Okay. So when you have a network of these miles, easily about 100, 200, 300,000 miles of pipe network. And sometimes these pipelines go through the field. There is no human beings around. So it's not that dangerous, but sometimes it can go under the, these are all buried pipelines. And sometimes they can be buried in a playground, a school playground. So if there is an explosion there can be children who can be affected. So it's very important to detect corrosion of these pipes, since these pipelines are buried about 6 feet underground, and if there's moisture, there is minerals, so this corrosion is very, very common. And you want to detect this, you don't have to dig up each time. So magnetic NDE methods are used over there, extensive. Okay. Okay. So, there are two kinds of problems. When I talk about corrosion in pipe wall, these are gross corrosion. These are of the order of, inches in diameter and depth. But at the same time, when you have sometimes in material, particularly in pressure vessels, say in the nuclear power plants or thermal power plant. You can have microscopic damages. There's something called creep damage and metal fatigue. Even aircraft, for example, when you have cyclic loads, high amplitude stresses, you can develop fatigue problem. And these kinds of fatigue due to cyclic stresses and strains results in crack initiation. And this happens at the grain structure level. And after repeated cyclic loading, this crack starts growing. It starts growing along the metal boundaries, okay, and that results in a lot of shear stress. And so there's a propagation stage 1 and stage 2. And ultimately, of course, the crack grows large enough that the material can fail completely. Okay. So, people have in the material science department probably have studied the crack initiation and growth at cellular level, okay, at microscopic level. And it's very difficult to detect them at microscopic level because none of our sensors are that sensitive. So what we do is all these cracks at the microscopic level affects some properties of the material. So indirectly, we try to look for changes in those properties and then determine and correlate that with the fatigue or amount of fatigue in this in the material. Okay. So one of the things that they've studied is in the crack initiation stage, there are cell structures formed. There are kind of domains that are formed and which hardens and become sources of stress generation. And this results also in what is called as persistent slip bands, and these things give rise to increasing the crack propagation and crack damage and failure of the material. Again, all these things happen at the crystallographic scale of the material. So we won't get into that anyway. Okay. So what it says is the slip bands, when you have cells and you have slip bands, and these slip bands, when it is really slip, they start that's how a crack is initiated. Okay. So it's always at the grain boundaries is where these things happen. So magnetic NDE method looks at how the magnetic properties of the materials are affected by these kind of microscopic changes within the material. Okay. And ideally what industry wants is to detect the cracks at the initiation stage, not wait till the crack has started propagating, because then it's more difficult to repair and fix the system. So they want to determine at the initiation changes. So basically, as I see over here, we are looking for NDE methods that are sensitive to the materials, how the properties change at when the microstructural changes. So we have worked in ultrasonic methods. One of all these materials that I'm talking about, in steel, there's also different types of steel. There's austenitic steel, there's martensite steel, where the crystal structures are different. When one martensite, they have elongated crystal structures, and austenitic is more rounded, and they have different properties. So martensite steel is what is used most of the time for structural applications. When there is stresses, sometimes there is phase transformation. Some of these fatigue damage can also result in changing from martensite to austenitic steel. And since each of these regions they have different properties. One of them is isotropic, the other is anisotropic. So we can look at, we have to have some kind of indirect methods, and magnetic NDE provides those indirect methods for determining those properties. Okay. So one of the techniques that we are using is ultrasonic. It's a combination of ultrasonics and optics. So when you have use ultrasounds, the ultrasonic wave sets these particles in vibration, and that also changes the thermal properties of the material. And fatigue also changes the thermal properties. So the rate of increase of temperature will be an indication of fatigue damage. Okay, because the thermal properties, a way of measuring thermal properties, and we use fiber optic sensors for determining thermal changes. Okay? Small rate of change of temperatures. So we have worked on, we have a faculty member who works on that. We have also worked on nonlinear eddy current. I'm going to talk about nonlinear eddy current because it's part of an eddy current method. We'll do that tomorrow. Today, what we will do is look at some of the methods that are available for determining such damage using just purely magnetic methods. We will talk about the magnetic flux leakage, the Barkhausen noise, and acoustic emission, magnetoacoustic emission. So, yeah. Yeah. Right. See, basically, if I don't know the quantitatively what to say, but basically the thermal coefficient or thermal change in a fatigue region would be different, whether it is smaller or higher. I am not able to answer that question because I don't know, but it is basically based on the crystallographic changes, the thermal property, inherent property changes, like a different material. So the coefficient is different. So if you have a baseline measurement, and this is like a monitoring problem, you have a baseline, you have a virgin material which is just produced, and you know what the thermal properties are. And then with use, you see how it changes in different regions. Does that, yeah. Oh, the ultrasonic methods, yes, it's a combination of ultrasonic and optics. Ultrasonic provides the excitation, okay? That's an ultrasonic wave propagation itself creates a thermal change. It's like you can also maybe use a laser to produce a thermal source and then see how that diffuses. So in this particular method that I looked at, that is basically is a method that one of our faculty members is working on. And you can use, actually what happens is when you have an ultrasonic wave, okay, and if there is a crack, most of the time the crack tips is where there is a lot of friction that takes place because of ultrasound and increases the temperature. Okay, and you look for, so you use ultrasound just for providing the heat energy. Converts the ultrasonic vibrations to thermal, and then you pick up the thermal incremental rate of increase by using fiber optic sensors. Because the strain, basically that changes the optical properties, and then you look at how that changes. And fiber optics are very, very effective, very efficient for thermal measurements. Even when curing composites and all that, we do look at use fiber optics for that. Okay, so magnetic method, so we need to know what is magnetism. And this is a picture of the hysteresis curve. So how do you characterize a magnetic material? I think I'm going to use my laser pointer here and sit down. Okay. So this is a magnetic hysteresis curve. I think everyone is familiar with that. So anyway, I'll go through that for completeness. So this dotted line is what we call the initial magnetization curve. You start with a totally demagnetized material. You have this, and so on the x-axis is your excitation input. How do you magnetize? And this is the flux density, which is due to the magnetism of the material. And so what happens is, if you look at any magnetic material, you have these domains, and each of the domains have their own magnetic moments, which are randomly oriented. And then when you apply the field, they all try to align with the magnetic field. So that's what happens when you have a magnetic moment and applied field, right? So they become parallel. So that's what happens in the flux density. The equations are given as a function of H as well as the magnetization. And at some point, everything is saturated, everything is aligned, and that's your saturation point, that is A. And then when you now reduce the magnetic field, so your excitation, look at it as a sinusoidal excitation. So you've got the peak, and now you start reducing it. And when here it's reduced to 0, but still there's some remnant field, and that remnance parameter is a function of the material. So that gives you information about the material. And then you have to reduce it further, make it negative. So you go down the negative side of the sinusoid till the B becomes 0. And this field is called the coercive force, or the coercive field. And then this is repeated when you make it negative, in the negative direction. All the moments are now pointing in the opposite direction and get saturated in the opposite direction. And then you go back, increase it again. You have E, the point E, and F, which are symmetric about the origin, and then this goes on. So when you have a magnetic material and you apply an alternating excitation force, it traces this hysteresis curve, which is really a loss of energy. The area of this hysteresis loop is the energy lost in magnetizing, demagnetizing, changing the domains and all that. So basically, we can see that this is a nonlinear phenomena. The way B is related to H is by mu, but mu itself is a function of B. We'll see that later. So it's a nonlinear phenomena. But this is basically the characteristic of magnetic materials. So for isotropic materials, the permeability, or mu, that you calculate is independent of the direction. It's the same in all directions. Okay, that based on the whatever grain structure and all that, you get that property. So this is actually this is an isotropic. There are two hysteresis plot. One is the B parallel, and the other is in two orthogonal directions. Okay, and be perpendicular. But if you look at anisotropic material, you can see that the permeability is so different in the two directions in the same material, because the material is not, the grain structures are not isotropic. So you have different type of hysteresis curve. Okay. So the permeability, the coercivity, the remnance field, they're all sensitive to microstructural properties. And using a hysteresis curve, you can determine the kind of stresses or strains or fatigue damage in the material. Okay, so that is one thing. And I think, yeah, let's see. This is difficult to read over here. So these three are the hysteresis curve with different levels of stresses. Yeah, it's not mentioned here, but those are how the hysteresis curves themselves can change with stresses. So you can look at these changes, monitor that, and determine the fatigue in the sample. Okay. So these are some of the things that you have to know for when you have, and again, these things changes with different grades of steel, different types of, and also there are materials which are functionally graded. So you can add some kind of ferromagnetic particles, and you can control how these things change for different types of applications. I know. This. Okay. So if I look at the magnetization, the important things to note here is this black curve is your initial magnetization curve that we saw in the hysteresis curve. And I can also plot at each point the mu value. You know, we can go back to this and look at for each H, you can also look at the B that is produced, the nonlinear B, and that B curve, B versus A, the mu versus H curve. This is the B versus H, the black one, and the mu versus H curve, because mu itself is a function of B, it looks like this. At this is at the linear region, it reaches its peak. And when the material gets saturated, okay, the mu it starts decreasing. And so that's what you can see over here in the blue curve. Okay. So at different values of Tesla, those are the different excitation, application, applied magnetic field at these points that you see over here. Those are the values. And so when it saturates, when there is saturation, complete saturation, it becomes practically non-magnetic. Okay, the material. So it goes down. Okay, and these are the things that you really need to know when you apply a magnetic NDE method. And you know, basically, you've got to know. Also remember that the flux, magnetic flux, will pass through a path of least reluctance. Okay, it's just a magnetic circuit is very much like an electrical circuit, and the flux forms closed loops, just like current, and the path of the flux is based on the resistance at each point. So we'll see that a little bit in this, how it is applied. Yes. Mm.
Constant.
Yeah.
The value changes depending on what is the field.
Right.
Which at 0 it has gone to the peak, and then after I have not even reaching my nonlinear, it started coming down.
Yeah.
At in the region where
yeah. Right. So basically, you know, the mu is the derivative of B with respect to H, right? dB by dH. So if I look at it as a piecewise linear, then I will say, oh, it's constant. This is a constant positive slope, and then here it becomes 0 when it's flat. When it's flat, it should become 0. And that's what you're saying, you know, right now. So that is intuitively, that's how it should change. And that's what we're seeing over here. We are taking the mu as the derivative of B with respect to H. Right. Yes, at each point, you're going to look at, you know, right now, at each point you take the derivative, and then this is how it looks. But you can intuitively see that, oh, this is almost linear, it should be constant. But when you take the derivative at each point, you really get a curve that looks like this. Yeah, what you're saying is absolutely right. But what the important thing to note is that we are looking at derivative at each local point and see how locally it changes with respect to it. And so when it flattens out, the change now becomes negative. Slope becomes negative. Which in oh, the derivative is infinitesimal, really. You know, mathematical derivative is very, very small, right? So as the interval goes to 0, you're taking the ratio. Then, you know, in the definition of a derivative, that's what happens. So Mathematically, you can look at the equations and calculate the derivative, but then if you have actual points, then, it could be, this could be a 0.1 Tesla. I don't know, how you can decide on any interval, okay, whatever, if you calculate numerically, yeah. Yeah, so important to note, that the mu goes to a maximum and then it reduces. So when mu is maximum, the reluctance is minimum, and as mu goes down, see, yeah. So and when mu becomes lower, then the reluctance increases. So higher the flux density, when the flux density is large, mu is small, and reluctance becomes large. So these are the things that you keep in mind. And you see over here, so this is the material, says the sample. Okay. So how does the magnetic flux leakage work? This is the sample. You can use a magnet or you can use a current to magnetize. And this sets up flux lines inside this magnetic material, right? It's a high mu material. And then suppose there is a defect on this side, outside. Either side is fine. What happens is these flux lines get scrunched up, right? Because there's less metal at where the defect is. When they scrunch, your flux density increases. And remember, flux density increases, permeability decreases, reluctance increases. Okay, so the reluctance in the metal increases. So some of the flux lines, the flux will always go through a path of least reluctance. It goes through the air. Okay, that's called the leakage flux. And that is why a leakage flux is caused. Is related to the underlying magnetic principles. So from that curve that you see here, you want to operate at this region where that's where the sensitivity is maximum. So you don't want to saturate the material. So that's what happens. So ferromagnetic, if you look at the different steps, you first magnetize using a permanent magnet or electromagnet. You set up the magnetic flux. Flux passes through the path of least reluctance. In the presence of defect, the flux will bend, will get scrunched up, and the flux density increases in the vicinity. Increased flux density means increased reluctivity, decreased permeability and increased reluctivity, and that causes the flux to leak into the air. And then you can pick up that leakage field. It's a very local field. You can pick it up using a sensor, like a Hall sensor. And Hall effect probes, basically, the Hall effect, I think we all know what that is. Yes, this is only for ferromagnetic. It will not work for anything else. Yeah. It is it is true, but okay, when you say mu of material is larger than air, but that mu, when you have a saturated magnetic materials, is like air. The mu of material is the same as mu of air. Okay. That's what saturation does. Yeah. Yeah. Well, but the thing is, yeah, I think let me show you. We have actually simulated it And you can see, yeah, definitely what you're saying is right. Compared to a region away from the defect, this is much, there is a more density. But you don't find the field, the flux lines going like this and taking a left turn, going to a region of lower reluctance, because ultimately the overall energy has to be minimized, or entropy of the system has to be minimized. So it goes, it's in the vicinity of the defect, it will leak into the air. Yeah. So this is basically a Hall probe, which using the Hall probe and the Hall voltage, you can detect the field in all directions. All three, you can calculate Bx, By, and Bz, okay, by turning it accordingly. So I won't go into that. These are simply Hall sensor. You can also use simple coil sensor, but a coil sensor will be useful if you have time varying field, because voltage is then induced in it. Or you can use GMR sensors, which is much more sensitive than and Hall voltage sensors. And I think now recently you also have a TMR sensor, which is tunneling magnetoresistive sensors. There are sensors that can detect very small field. And SQUID, which is a superconducting quantum interference device, which can detect very small fields. So once you set up the leakage field, then you can pick it up and then analyze that field for. So what we have here, this simply shows the flux, for different types of excitation. You have an encircling coil that will produce a magnetic field in this direction, or you can just pass a current in this direction, will have a circular magnetic field and all that. And again, depending on the application, you can do different methods. Yeah.
This sample can be of any kind.
Exactly.
My question is, sample can be of any kind, and system is already there. Every time I have to tune my sample, because their stress conditions will be different.
Yes.
So it may happen that I may saturate
Yep.
unknowingly. If I'm not knowing the complete physical sense
Yep.
of sample,
Yep.
how I can.
Right. That is what I said yesterday. There are commercial systems available, but you can't take a system and apply it to a sample. You have to go through, okay, for this particular sample, this is the magnetic property, this is the shape, size. You have to modify your system. That's why commercial systems can seldom be used as is for any application. And that is why, or we do get a lot of projects. There's a lot of opportunity to get NDE projects, because in most applications they can't just use a commercial system and try to get the result. You have to understand all these details, optimize your system, the sensor, how much to use, how much field to apply. So what we normally do, and that I'll talk about in the afternoon, we do a simulation of that whole thing. We get a full understanding of how the flux is distributed, how from the flux distribution, I know what the mu value is at each point. And then I know what to apply and how to pick up that's a very valid question, yeah. But it's all that is very important. And yesterday, that's what I was trying to tell, that you have a lot of commercial systems, but we still, people cannot just use it unless for very simple problems. But when you go to for a pipeline inspection, you really need to know how to use it intelligently and in the best way. Yeah, those are all things. And that's why I went through all these, initial things. You're right. Okay.
Sensor is not in contact. But the bridge that we use in the magnet.
Yeah.
has to be in contact with the sample.
Yes, for completing the magnetic circuit. If you use a magnet, okay, you can also use current. You can, depending on, again, how, in what direction it should be magnetized. If you have, if you need the I'll talk about that also in the pipeline. If you magnetize it in this direction, then your current has to be, encircling, a coil's encircling. In which case you don't really need contact, but the magnetization itself is one time. It is set up and that's it, and then you're scanning for leakage field. So that is what determines if it's a contact method or not. And because leakage fields are so local and they're pretty small level fields, you really need to be very, very close to the sample to pick up, to be sensitive to things.
Transmitter or a sensor which you will also be having, that means if it is able to detect magnetic fields, there is a possibility that might also, though the quantity will be small, but it will create a magnetic field. Or it will generate, with the above magnetic field, it will generate current sort of thing.
Yeah, see, generally what happens is you are only picking up one component of the magnetic field. So those sensors are the small GMR and Hall sensors are small. And so when you're looking only for one direction, so they may not produce field in the same direction, okay? So, because the excitation current produces a magnetic field, and then the leakage field is also a magnetic field. So that's why you have to make sure that these two fields are in independent directions, orthogonal directions. And that's what we saw even in this example. So this is the input magnetization is this field. And in the leakage field also, what you do is you just pick up the normal component at each point, okay? So there is no interference between primary and secondary fields. Yeah. Yep. Yeah. If there's air gap, what? Air gap inside the material is what we define as a defect, right? I am sure. So you're talking about air gap when you're in the material?
Yeah, in material, air drop.
Yeah, so that is a defect, right? So basically, if you look at in this case, it's a metal loss. So you're saying it's a manufacturing defect that there is some kind of an air pocket in the material. You can detect that too. It's possible because see, it's like a ripple effect. The flux will start bending, okay, and there will be a little bit that will leak into the air. Compared to, see, for example, if the air pocket is somewhere here, this is an exaggerated picture here, but if the air pocket, compared to a region where there is no air pocket, there will be a leakage. So if you take some kind of a differential measurement, you can definitely pick it up.
MRI scan is like this.
MRI? Oh no, MRI is quite different. It's there are a lot of coils for excitation coils, and you are trying to excite the moments of certain hydrogen molecules that maybe, it's very complicated. MRI is a very complicated scenario, and don't want to get into that, but it's pretty, they use a bunch of coils, different types of coils to focus, and over there, they don't measure field, they measure the moment, they have recession and precession, different motions of the magnetic moment of molecules, and they pick that up, okay? So it's a very complex and method. So That's a whole semester long course on how to do that. Okay. Okay. So all these issues, how do I, depending on, one thing to note is, in order to detect a defect, your defect has to be somewhat has to cut the flux. If your defect is in the same direction, you're not going to detect it. So all that you have to take into account. So in this, we have all these pros and cons. It's very a simple method for surface and subsurface, low cost, it's rapid because it is non-contact, and no surface preparation is needed. In many of the other methods, you have to make sure that there is it's cleaned up and all that. We don't need to do that. But the disadvantage is that, of course, material has to be ferromagnetic, and it's not sensitive to the certain orientation of flaws. And the other thing is, once you do a magnetic flux leakage, the whole specimen gets magnetized. So if you want to do the next time, you've got to demagnetize the whole thing, all that. And as we pointed out, you need operator experience to think about all these different issues and make sure that you optimize and then you interpret it correctly and all that. So in this, you have a defect shape. If you have an axial magnetic field, if you have this very thin, then you have a weak field, the flux leakage intensity. When you have a fairly big but vertical direction and the magnetic field is in this direction, you have good. If it is very round, again, this is kind of a orthogonal as also. It has a big component. It is parallel to the field. It's stronger. It becomes smaller. This becomes weak, and this you cannot even detect. Okay, this also. That's another thing that you have to keep in mind. So, so that's basically discusses different issues in the magnetic flux leakage method. So the experimental setup is shown over here. Once you magnetize the field, this field is an amplified, filtered, processed, you digitize and then store it. And this actually is a simulation image, okay? And if you look at the magnetic, if you just look at the normal component, you will have, because you have something that goes like this, here the derivative is positive, here it's negative, and that's what your normal component looks like this. Okay, and for the entire image, when there is a defect, you can see everything. This is simulation value. Okay. The underlying governing equation for this is a static elliptic equation. And okay, so basically you have the Maxwell-Ampere law for setting up the magnetic field. Normally, we derive the governing equation in terms of the potentials. Again, we'll talk about this more in the modeling, forward problem modeling class. And then you've got to use the constitutive relation with J is sigma E, and in terms of magnetic vector potential and so on. Anyway, I think I'll skip through this because we'll come back to it when we talk more about modeling itself. But this is the governing equation. This is the equation that we need to solve, the final equation for simulating a magnetic flux leakage. And here is a numerical model, and we just saw this thing. So this is the sample geometry. The sensor is here, and this is the defect, metal loss defect. And this is the magnetic field image, flux leakage image that you can get from a simulation model. Very similar to the so this is for a flat geometry, and for a pipeline, which we will do in the afternoon, we have very similar problem. So over here, you have, these are the magnetic pole pieces over here. So you do magnetize axially, and then this is an array of Hall sensors that can pick up, and then as the inspection tool moves inside, you can generate an image that looks like this of axial component. Again, we will talk more about it in the afternoon. Okay, so that is about magnetic flux leakage method. So another method that is used for, again, particularly for the microscopic damages, okay, type of thing, is what's called the magnetic Barkhausen noise or the magnetic Barkhausen emission. These are the same. Some people refer to it by different names. So what is Barkhausen noise? So when you look at the principle over here, we've seen that there are domains with random orientation, and when you apply a magnetic field, there are movements of the domains. When they align with the magnetic field, the domain walls move. And the domain wall movement is not a continuous smooth movement, it is discontinuous. Okay. And again, this discontinuous the movement or the restructuring of the domains is sort of controlled by what are called as spinning sites in the crystal structure. These can be dislocations or impurities in the crystal structure. So they all make this domain movement very discontinuous. And so with this, each discontinuity provides a little signal. Okay, so it's not a continuous signal, it provides a signal that looks like this over here. And this noise, you can use, so the signal, the voltage that is generated is a noisy signal. It's not a very smooth signal. So when you look at this particular derivative of this, you can get the Barkhausen noise signal. We call it the Barkhausen noise. So this is the near field, and when the low field and there's high field, you can see how the domains are moving quite a bit. Okay. Okay. So the Barkhausen effect consists of discontinuous changes in the flux density. It's the same based on this hysteresis curve. And those are due to jumps in the domain walls. And they give rise to, it's almost, you can hear it. You can hear the clicking sound. And that's the Barkhausen emission. But if you convert that into an electrical signal and plot it, you can get a noisy signal. The motion, it's irreversible motion of the domain walls when they break away from the pinning side. So if you get into the details of the crystal structure, that's what's happening. But in a gross level, when you are actually picking up the signal, you get a noisy signal corresponding to this particular phenomenon. Okay. So for an MBN, okay, you can see the structure here. Here is your magnet, and you have basically a Hall element that is then amplified. You have a wave generator for producing the magnetic field. Okay, and there's a pickup coil, excitation coil. You can see the big thing. And amplified signal from this pickup coil is the MBN signal, which can be then used for interpretation. Okay. So I'm just going to show the time domain signal that you get. So for each cycle of the excitation signal, you can, from the pickup signal, this is the kind of signal that you produce. The blue is the Barkhausen noise, and you can also have a red signal here, which is the magnetic field that is applied. So Barkhausen, there is nothing more to talk about it. I think I should leave this for the afternoon because I'm going to talk more about this in the afternoon. Well, it doesn't matter, then we won't do it in the afternoon. Okay, so we saw a Barkhausen noise signal. So what kind of information you can get from there? So this is taking one particular cycle, stretching it out. You have okay. So basically, we look at the, we saw the signal, we just look at the envelope of the signal. And from the envelope, what we're seeing over here is that we are picking up some features, okay? The noise, the positive envelope of the one period of the Barkhausen noise is what you see is in yellow over here. And the blue is the actual applied envelope. And you can fit some kind of, so what we are doing here is we are taking the envelope and we are fitting some Gaussian curve. Actually, you fit in Gaussian mixture envelope. So this is basically a method for extracting a quantitative feature from this very noisy signal that you see over here. Okay, so that's what we are seeing over here. This is some work that we did do for the nuclear industry, because we have these turbine blades which are, go through a lot of mechanical stressing. What we see here, where is the picture? Yeah, this is actually a turbine blade over here that from the power plant, and we're looking at fatigue damage due to vibrations of this. Pardon? Yeah. We actually magnetizing with a yoke in that, right? Yoke, magnetic yoke. Yeah. So that, yeah, this is the experimental setup. So this is the yoke over here, and we're just magnetizing. Yeah.
The AC current will pass through
Yeah.
that coil. So it is sinusoid. So I would just I'm just curious that rather than passing just a normal sine wave or a sinusoid, if we make it as an amplitude modulated or a frequency modulated wave, pass that, will that result in some? I mean to say that can that accuracy be increased by changing that excitation?
See, for your frequency can't be very high, because your domains are the domains are flipping and all that. So you want it there to be. You typically measure.
That I mean that in case of making it as an amplitude modulated wave, the amplitude will change at some instant of time, and then again it will reduce.
Yep.
Will that increase the just?
I don't know. I don't know the offhand. I'm not very sure it will. I think this is quite an established procedure, and I know the person who developed this has done a lot of work, and he would have probably come up with that thing. So that's my basis. But it's a worthwhile looking into that, and maybe at least it will give you a paper to investigate different type of excitation signal for Barkhausen. Yeah, I'm not very sure about that thing. I haven't given it much thought. Maybe we can discuss this more. Okay.
That there could be some, and that would be
Heating effect of the coil or the sample? Sample. Yeah, hysteretic heating, because you are. Yeah, there is some. Yeah, there has to be some hysteretic heating, but when you do for say 5 cycles and you stop, you don't heat for too long, so it's not something that's going to affect the signal. Typically, we do use a pretty low frequency signal for going through the hysteresis loop, but there's no reason why you can't increase. But my feeling is that the ambient signal itself, how it varies with frequency, I don't know. It's always been done at low frequencies. So I've been thinking there has to be a reason for that. Never done at high frequency. But we can try. Thickness of the material? It is, it's like almost an inch thick. You know? Yeah, well, this is also a surface or near surface. You know, I don't think it can go because very deep, because you know you're looking at if the defect is down there, the leakage flux at the surface is going to get smaller and smaller. So yeah, and it has to go. But you can see that, you know, we'll see in the pipeline, if you like, where is that other picture that we had? There is not even this. Yeah, if you look at this, the defect is on the other side, but this thickness has to be small enough. Yeah. So that's why we had right direction. Yeah. So again, it's surface and near surface. When I say subsurface, it can't go like half inch. Yeah. Okay. Yeah, so these are, we talked about this thing. Again, these are, you know, these are slides for a very particular, for that particular sample and the work we did with that sample. And so basically this is the sample, okay? And this is where you're looking at stress regions, and this is where it gets fatigued. So basically we look at measurements in this area and see whether there is a, you know, subjected to say 100 cycle loading 100,000, you know, different number of cycles, and see how things change. And what we showed here are different features, okay, that we look at for that. We take the signal, we take the spectrum of it, and we look at the peak value here, peak amplitude, and the frequency where the peak occurs. I mean, these are features that you see over here, and what's the energy in the signal itself. And those are the signals that are used for looking at fatigue damage. And it's a difficult problem. And the reason for that is, even though you calculate all these quantities and measure, nobody knows what the ground truth is. You know, how do you characterize? You can say that, okay, I've stressed it for 50,000 cycles or 500,000 cycles. And when you have that kind of a difference, you can say, okay, this is probably under more fatigue damage than this. But sometimes there are manufacturing defects, and a sample which has gone through 100,000 is much better than something breaks at 50,000 cycles. So there are some our final features. There is some trend that we see, but the variation in each is pretty large. And so we have left it at that. Maybe we said we have to look at other methods. So the next slide shows the drawbacks. So MBN is a method, but I am not really in favor of this because there is a lot of unknowns in the usage of this method. So you can, under some conditions, you can look at the residual stress of the surface, but the surface conditions can also change by carbon contents, and there are case hardening. Case hardening is a deliberate method. You know, in the automotive brakes, for example, you have steel systems. You want to use case hardening for making it stiffer and stronger. And so there are some kind of applications where MBN is used. phase transformation from austenitic to martensite. There is, because of the fact it is anisotropic, you can. But a flux leakage will also do the same thing. And in general, my choice would be to go for flux leakage than MBA. But I thought I'll just talk about it because it is one of the reported methods. And there is a group of people who that in Wales, there is a center for magnetic materials where they do a lot of Barkhausen noise. Okay. So criticism of Barkhausen noise is a poor repeatability and stability. You saw how noisy the signal is. To reproduce the same noisy signal is very difficult. Each time is going to be different because one of the reasons is the magnetic history. You know, when you apply the field, you've got to demagnetize again for doing all that. So anyway, just for you to be aware of one of the magnetic methods. Okay, so magnetoacoustic emission is very closely related to the magnetic Barkhausen noise. And I said, when you have those discontinuous jumps, it also, there are strains in the magnetostrictive, there are magnetostrictive strains because these are where the material itself expands and contracts because of applied magnetic field. And for those kind of methods, you can, there is a magnetoacoustic emission signal, and this can also be picked up and analyzed. Again, not a very popularly used methods. This is the experimental setup. You have the same kind of thing, except that the pickup sensor now is an acoustic sensor, okay, because it's looking at mechanical changes like in the materials because of magnetic field, and then picking up the acoustic signal from that. Hey, where was? Pardon? The free excitation frequency is very small. Okay, it's not very large because, but the acoustic signal that is produced is in the acoustic frequency range. So, like 4 kilohertz or up to 20 kilohertz. It's not very high frequencies. So those are basically, you know, the magnetic NDE methods. I'm wondering what's the time now? Close to noon. So I think we can stop here. We can just, if you have any questions. Again, magnetic materials, as I said in the beginning, their application is very limited because it has to be magnetic and the defects have to be surface, near surface kind of thing. But at the afternoon, we will, you know, in the pipeline inspection, there are ferromagnetic pipes that are buried underground. Magnetic methods are very much used by industry. And we'll go over that in the flux leakage method in the afternoon. Just an example. So today is going to be a short session because it's not a very popular session. And when you come to eddy current, it's going to be a lot more versatile. It is much easier to, and you know, even though eddy current is just a coil, we'll see how you can design different configuration of coils to achieve different results. And that's more interesting. That's tomorrow. Okay, is that? Yeah, or you can get even higher. I said 4 kilohertz because it's called acoustic. Magnetoacoustic emission is an acoustic frequency.
Sample property itself.
Why?
Because magnetizing, demagnetizing very.
Yeah, so it goes through the same. That's why you have a hysteresis loop, right? So it is cycling through that, you know. In all these transformers, in all these power systems, you do have hysteresis happening. And you also can hear the acoustic, the emission in those transformers. So I don't think it changes. But although, again, what I said was the pickup signal is in the acoustic frequency range. You don't have to magnetize at that higher frequency. You can, yeah. Right, right. At 50 hertz, right, exactly. You can. That's why the acoustic frequency is much higher than the excitation frequency. So when I said I didn't say 4 kilohertz is for the excitation signal, but it's the pickup signal. Well, that's, if you look at this particular thing, here, if you look at this is the excitation frequency, each one is a cycle, and that is much lower. The pickup signal you can see is very high, the high frequency. And if you look at the frequency, need my glasses out here. So out here, this is the frequency. I don't have the right units for my x-axis, but I can find that out and tell you that that's the when you take the spectrum of the received signal over here, you can see that the frequency is much higher for these than the excitation. Okay. So that 4 kilohertz or 20 kilohertz for the pickup signal, because it's a totally different physical process. You've got magnetic field excitation, and the pickup field is an acoustic signal. So it's different, totally different. Okay. So okay, let me see. No, it's not. This is a different physical process. This is the domains which flip because of the applied magnetic field. And that flipping is not continuous. Like, when I first talked about the hysteresis curve, it's a continuous flipping, they're changing the orientation. But in practice, what happens is because of the crystal structure or the domain wall, there are impurities or dislocations. So because of that flipping of the domain is discontinuous. And that discontinuity is what produces the acoustics, and not vibration.
Any questions from the online students? And you can unmute yourself. Okay, okay. So we'll wind up now and we'll meet at 2:30.
Sharing these slides.
Yeah, I'll share. Actually, yesterday itself we were discussing that for the handouts.